we've been looking at UNIX system calls. We looked at fork, which creates an identical process to itself, exec, which replaces the current process by another program, wait, exit. Exit basically allows a program to finish, a process to finish. Wait allows one process to wait for another process to finish. Right? Then the other types of system calls we saw were open, which opens a resource. So it and so name, permissions, which opens a resource and returns a file descriptor. Right? And then we looked at read, file descriptor, some buffer, size. We looked at write, once again file descriptor, buffer, length. Okay, and something on the screen. How do I put it off? And close. Right? Okay. Good. So we looked at all this and we said, look, every process T on the system has a file descriptor table, which the process cannot access directly, but it can access it, or it can manipulate its entries using open and close calls. Right? The first three file descriptors are special. stdin, standard input is 0, standard output is 1, and standard error is 2. All other file descriptors are not special, in the sense it doesn't matter what the number is, right? There were questions last time. If I want to open the if I want to set an entry, the 15th entry, how do I set it? Well, if you wanted to set it, you could open everything till 15, and then call open 15 times, so all the entries get filled up. Recall that UNIX fills up the entries starting from the beginning, right? And then you can close all the entries in the middle by saying close, whatever is not 15, you can just close it. So that way you'll have a table which has only 15, but it's actually not important, right? Because the number 15 is not important. It doesn't matter what the file descriptor value is. What matters is that there is some file descriptor value which points to that resource. Okay, except for 0, 1, and 2, which are special. 0 is for standard input, 1 is for standard output, and 2 is for standard error. Okay, so let's see what happens when you're running the shell on your monitor. Right? So if you're running the shell on your monitor, and let's say you are using a keyboard to enter commands, then typically the shell's FD table would be 0 will be pointing to keyboard, 1 will be pointing to monitor or console, and 2 will also be pointing to monitor. Right? This will be the typical setting of your running shell, common setting, right? And all these 3, 4, etc. will not have anything. They'll be all empty. Right? So that will be the typical setting when you're running shell on the monitor. On the other hand, let's say if you were running a shell script, right? So if you would say, for example, shell, let's say sh, and you say some commands. Right? So in this case, the file descriptor table will be or something like this for the shell. Zero will now point to the file commands. Instead of the keyboard, it's now pointing to commands, right? And 1 and 2 are still pointing to the monitor. Right? So this is one way of implementing shell scripts. So the commands file could be a shell script which has one command after another, and if one and you know the way an operating system will implement something like this is just point the standard input to this file, and so it's going to just take one command after another from the file and execute it. Instead of taking commands on the keyboard, it's going to take the commands from the file. All right. Okay, so this kind of method gives a very composable way. Another example is, let's say I was running a remote shell over over the network, right? So let's say I am doing SSH, right? So in this case, the standard output of the shell need not be the monitor, but it could be the network. Right? So it's the same program, you just change its environment from the local monitor to the network, and so you can implement a remote shell. Right? So this kind of organization where you have a file descriptor table, and the file descriptor table could point to different resources, gives a very composable way because the program logic can be separated from the program's environment. The environment could be keyboard or input file or output file or network, and the logic still remains the same. Right? Okay. So let's look at a concrete example. On the shell, let's say when you type ls, right? I'm sure all of you have typed the command ls sometime. Ls basically lists the contents of the current directory. All right. So the way ls is implemented is ls points to a file called /bin/ls, which is an executable file. Right. When you type ls, what happens is the shell will. So let's say this was shell. Right, and what it does is it calls fork and then exec to create another process called ls. Okay. And ls basically, because the other semantics are that whenever you fork a process, the file descriptor table gets copied to the child process, right? So this is the parent process which called fork, and this is the child process which got forked, right? And the file descriptor table of both will be pointing to the same location. Right. So for example, if you were executing the shell in with standard input pointing to keyboard, I'm writing KBD for keyboard, then even LS's standard input will be pointing to the keyboard. All right. One, if the standard output was pointing to the monitor, the standard output of LS will also be pointing to the monitor. Right. So in that sense, you know, when you type ls, depending on where your shell was running, ls basically outputs its information to exactly the same place. So if your shell was running over the network, when you type ls, the content output of the ls file, LLS program, also gets streamed over the network. If you are running shell over the console, over the monitor, then output of the ls program also gets printed to the monitor. All right. So because you just copied the file descriptor table from the parent process to the child process, the environment of the child process is identical to that of the parent process. Right. So if I was to look at the code of ls, so let's say ls code, right? It will do nothing but say, okay, write 1, comma, whatever the contents are. Directory contents. Okay. I'm omitting some syntax, so there's some size and where does it get directory contents from. Let's ignore all that. But basically inside the ls program, it will be making the write system call, and it will be making it on file descriptor number 1. The file descriptor number 1 is not initialized by ls itself. The file descriptor number 1 was inherited from its parent. So if the file descriptor 1 was pointing to the console, then I will print the directory contents to the console. If the file descriptor number 1 was pointing to the network, then I'll print the directory contents to the network, and so on. Right? So that allows, once again, it allows composability. Right? Each of these programs, ls, shell, echo, cat, these now start acting as utilities that can be composed one on top of another. And because their environment gets set by whom they are composed with, they can just, they don't need to worry about the environment. They can just say the semantics of LSR that it will print the directory contents to its file descriptor number 1. It doesn't matter where file descriptor number 1 is pointing. It could be pointing anywhere in the world, right? LS doesn't care. LS says I'm going to write these values to file descriptor number 1. Right? So that way the program ls gets completely separated from its environment. Similarly, the program shell gets separated from its environment, or any of these programs, right? So this division of environment and logic is gives a very nice composability, and that was one of the great features of UNIX, which made it very popular, and those features continue in modern day operating systems like Linux or Windows, right? So that's why we are talking about them today. All right. So let's take another example. Let's say I'm on the shell. All right. So this is the shell. The $sign basically means I'm on the command prompt. And let's say I say ls, and the command shell, let's say the born again shell or any other shell that you may have used, command prompt on Windows, allows you to redirect the output of ls to something else. So you could say ls greater than out. What this means is that the directory contents will not be printed on screen, they will get printed to this file called out, right? So let's see how will the shell implement this kind of redirection. So this greater than sign is something that the shell understands, right? So what the shell is going to do is it's going to read this command, it's going to figure out that there is a greater than sign in the command, and based on that it's going to say, okay, this is where the redirection needs to take place. And so before it starts ls, what it's going to do is you want something like this, that shell is, let's say this is the shell whose standard output is equal to monitor, right? But you want to start another program called ls whose standard output is not monitor. In this case, it's instead this file called out, right? So previously we saw that whenever you type ls, the new program has identical file descriptor table, right, as the parent. So if the standard output of the parent was monitor, the standard output of the child will also be the monitor. But if you specify this greater than sign, then the shell reads this command, figures out that you want to do some redirection. So this is called a redirection. This is called an output redirection. It figures out that it wants to redirect the output to something else. And so what it needs to do is create a file descriptor table for the child process in which the standard output is now pointing to this file out instead of pointing to the original standard output of the parent, which was the monitor. Okay. So let's see how something like this can be implemented. Well, it's very simple. If you type ls greater than, let's say, out, then what the shell will do is, just like before, it will call fork first, right? And it will check if PID is equal to 0, then I'm the child. The slash star is basically a comment, and what I'll do is I'll call exec on ls, right? But before I do that, I will manipulate file descriptor table, my own file descriptor table, such that using the close and open calls. So before I do that, what I'm going to do is I'm going to say close 1. That's going to close my standard output, and then I'm going to do open out. Okay, I'm omitting some syntax regarding permissions, etc., but just for simplicity. So when I say close 1, what's going to do is, let's say this was the file descriptor table. This is 0 and this is 1. Earlier, let's say this was pointing to keyboard and this was pointing to monitor, right? What it'll do is it will close 1 will remove this link and make this unused. And open out is going to look for the first unused descriptor, in this case it's 1, and it's going to point it to out, right? So what I've done is, when I forked, the file descriptor table from the parent got copied to the child, but then before I called exec, I changed the entry number 1 by calling close followed by an open appropriately, right? And then I call exec. Exec is going to run ls. ls is going to say write to file descriptor number 1, and because I've changed the environment so that 1 points to out, ls is now going to be writing to standard output. Oh, the file number, file name called out. Okay, once again, the shell is going to see, let's say this is the command ls greater than out. So it's going to check if it's a redirection, and if so, before it starts the new process, it's going to replace std out with file out. Okay, and the way it does is it basically says close on file descriptor number 1. Recall that 1 is basically std out, so that way whatever is the current value of std out gets wiped out, and then you say open out, right? Let's say in write mode, right? And so that replaces the file descriptor number 1 with out, and then you do exec ls, right? And so ls is going to now run with this new environment in which the standard output points to a file, right? And so what's going to happen is when you type ls greater than out, you are not going to see any contents on the screen, right? You're only going to see the next prompt right away, and all the content, all the directory contents, all the things that the ls program printed are now printed to this file called out, right? You can, replace this with any other program. Let's say program ABC, right? When you say program ABC greater than out, it basically means run the program, but replace its standard output with this particular file instead of using my standard output. So this is called output redirection. Okay. All right. Similarly, you could say ABC. Let's say ABC is the name of a program, and you could say instead of greater than out, you could say 2 greater than out. Right. This is also a shell syntax. And in this case, what you're doing is error redirection. So in this case, what it does is it replaces stdr, standard error file descriptor, and makes it point to out. Okay. So what happens here is that ABC's file descriptor table will look something like this. 0 will point to keyboard, assuming that you were running the shell using keyboard and monitor. So 0 will point to keyboard. 1 will point to monitor, just like before, just like the shell. But 2 will, the file descriptor number 2 is the one that will get redirected to this file called out. Recall that in the shell, both of them were pointing to the same monitor. But now if you do this, then you are redirecting the standard error to a file, and standard output is still going to the monitor, right? And how would you implement something like this? Well, very simple. If you have ABC2 greater than out, the shell will check everything, and then at some point it's going to say close to open out in write mode, right? And so that's going to change the file descriptor table, the environment. And then once you have changed the environment, now you can call exec ABC. Right? So now ABC is going to run, and but it's going to run with this new environment. And so whatever is the error message, that will go somewhere else. So often you may want that the error message should come to my mobile phone, but the normal output can just come to the console. So if you want to do that, you will just say ABC2 greater than mobile phone, right? So you want to be notified of any error condition even when you're sleeping, so you would do that. You just say redirect the error port to somewhere else and redirect the output port to whatever was in the shell. Okay? All right. So this is a good illustration of why fork plus exec is a nice way of spawning processes. So recall what we did was we first called fork, which created two processes of the same thing, right? So it created spawned a child. So it gave a parent a child, and within the child, I called exec, right? And there was a question in the first lecture: why are we doing this? Why are we having separate fork and separate exec? If I just wanted to create a new process, then why didn't I just create a new process? Why didn't I have a system call that create a new process, right? Well, separating this into two things allows you to do things in the middle. So in this case, for example, I changed the environment, recall, right? So what I did was I called a fork. Now I had two processes, and before I called exec, I called open and close, right? So I first called close, open, and then I called exec. So because I have separated fork and exec, I can do a few things in the middle to change the environment. For example, I can change the file descriptor table, right? That allows me to implement redirection, output redirection, error redirection, and so on. So separating into fork and exec allows you to execute more system calls in the middle, and that allows you to do other things. On the other hand, recall that I told you in one of the previous lectures that Microsoft Windows does not use fork and exec, but it has a system call called create process, right? Where you give the name. So for example, the name of the executable ABC, and then you give other things, but you also need to give all the environment. For example, what are the file, you need to specify the file descriptor table explicitly by hand, right? And this makes this system call very large. There are roughly 10 arguments that the create process system call takes. So it's a decision, it's a design decision. UNIX initially decided to have two separate system calls, fork and exec, that allows the system call interfaces themselves to remain very small, right? And so it becomes very easy and intuitive. And you can, if you want to change the environment in the middle, you can change the environment between you call fork and exec. But if you're calling if you have a system call called create process that's going to do everything at once, then you need to have multiple arguments to this create process system call, which makes it bulkier and clumsier. Okay. So here's a nice example of why separating creation of a new process is separated into fork and exec because it allows you to change the environment between the two system calls. Okay, there's a question from CEM. In Linux, all 0, 1 and 2 are pointed to the same devices. What is the significance of that? No, so it's not true that all 0, 1 and 2 file descriptors are pointing to the same device. 0 will always point to an input device, right? Like a readable file or the keyboard or an input network connection. On the other hand, 1 and 2 can potentially point to the same device, right? Standard output and standard error. But the reason they have given it separately, the two streams. So there is one stream of data coming into standard output and another stream of data coming into standard error. What Linux does is it merges both of them, and so you see all of it on one device by default. All right. But if you wanted to separate it and say, oh, I want output in console and error in network, let's say over my mobile phone, you are free to do that. And because the Unix designers felt that it's going to be a common thing that you want to have a separate redirection for output and a separate redirection for error, they have two different file descriptors, 1 and 2. Okay. All right. So we have seen how the Unix system call interface, and we have also seen what they mean, open, read, write, close, and we also saw how they can be used to implement redirection and before you execute a new process, right, or create a new process. Okay. All right. Let's look in more detail at how what are the contents of this file descriptor table. All right. So on Unix, let's say this is the file descriptor table. Okay. So let's say file descriptor number 1 is pointing to a file, right? Let's say it's pointing to a file out. What kind of structure is stored inside the operating system to say this? So it's actually pointing to a structure which first contains a pointer to the resource. So in this case, the resource is this file called out, let's say. And it also contains a number which says offset or current offset, right? So when you say write on 1, hello, 5, what happens is the operating system goes through this link, figures out that it's a file, figures out what the current offset is, and writes these bytes hello at the value current offset. So what happens is, if this was out, let's say this was the file out, then if current offset is here, then it's going to write hello starting here. Okay, and it will update the current offset to point to this place. All right. So the semantics of write in this case are that it will not just write the string hello at current offset, but it will also increment the current offset by 5. Okay. Okay. All right. So let's see what happens. Let's say I am executing the shell, right? And I say, and the shell was executing. Let's say this is shells FD table. 0, 1, 2, 3, and so on. And let's say 1 was pointing to this file called out at offset 100, right? Then let's say shell at this point called fork, right? And then called exec, and now there's another program called ABC, right? And this is ABC's FD table. Recall that when you call fork, then the entire FD table gets copied as it is. So even in the ABC's FD table, you're going to have 0, 1, and 2. And in this case, again, 1 is going to be pointing to the same structure, out and 100. Okay. There's a question here from BMSCE. Does current offset values are defined by the OS or by the user? Who defines the current offset value? Right? So when you open a file, depending on the mode you open the file in, the offset gets initialized. Right? So for example, if you open the file in write mode, the offset gets initialized to 0. Then as you call write or read on this particular file descriptor, the offset will keep getting incremented. Right? There are also system calls which allow you to modify offset, like seek, right? So for our purposes, let's just assume that open is going to initialize the current offset to 0, and future calls to read or write are going to increment the offset accordingly. A user cannot directly modify the offset value. He can only manipulate the offset values using system calls, right? Recall that all these structures, file descriptor table, and where they point are not visible to the user. They can only make system calls to manipulate the values of these structures. Okay, so let's come back to our example. So there was this shell that had this file descriptor file out open, and the current offset was 100, right? So for example, the shell may have called write on the standard output a few number of times, and let's say the offset is already 100, and now you spoke another process. So because you just copied the entire file descriptor table, the ABC will also get ABC's file descriptor table's standard output will also point to the same structure at the same offset, right? So now if ABC calls write, so let's say ABC calls write on file descriptor number 1, and shell calls write on file descriptor number 1. What will happen is both of them, the output of both of them will get interleaved, mixed, right? So let's say he writes hello, 5 characters, and he writes world, again 5 characters. So what you're going to see is in the file you're going to see hello world. Or depending on the order, you may actually even see world hello. Right? So basically, because the offset is getting incremented, both processes don't need to worry about what the current offset is. The semantics of the write system call are that whatever is the current offset, at that point write this string. So if two people happen to point to the same file, if two processes happen to point to the same file, their outputs will get intermingled or interleaved, right? So this is hello and this is world, right? Or they can, depending on in what order they executed, world could come first and hello could come second, right? So this is one way of sharing between processes. Okay. You have the same, you had your file descriptor table, the file descriptor table was pointing to serve some resources, then you forked, and because fork copies the file descriptor table, the child's file descriptor table will point to the same resources. And so, this is one way of communicating across processes. Right? For example, one of the process could write to this file, and another process could call read on this file to read whatever the value is. written by the previous the parent process. Okay. So recall, we said that in Unix, every process lives in a separate box, right? This is shell, and we said it has private memory, and this is ls or ABC, and this has private memory. And we said these programs can communicate with the operating system using system calls, but we never talked about how these programs may want to communicate with each other, right? We don't have any way of two processes so far communicating with each other. Well, it's almost for many reasons it's desirable to allow two processes to communicate with each other, and we are going to see more examples in future. And so this methods of allowing two processes to communicate with each other are called inter-process communication. Inter-process communication. Okay. So let's say this is shell and this is ABC. They cannot just talk to each other because they are living in private memory. But one way of them to talk to each other is to basically talk through the operating system. So he can say, I want to send a message here. So he's going to send it like this, and he's going to give it to him, and he's going to send a message to him. So this is one way of inter-process communication. And what we saw in the previous example is one way of doing inter-process communication. Okay? Because they are sharing the same file, they're sharing the same file, one of them could write and another one could read. Right? One of them is going to make this write system call, and the second one is going to make the read system call. Of course, there's a matter of, how do you decide the offset? So there's another system call called seek, which allows you to say, so seek takes a file descriptor and an offset value, and it basically set the current offset of the resource pointed to by file descriptor fd to this value off. Right? There's another system called seek. Right? So using write, read, and seek, two processes can now communicate with each other. All right, this is one example of how inter-process communication can be done. Here is another example of how inter-process communication can be done, and that is using the exit and wait system calls. Right? So the exit system call actually takes as argument a number, right, which is called the exit code. All right? And so the process which calls exit can supply a number which is called its exit code. So for example, an exit code could be 0, 1, 2, any number. Okay? And when you call wait on then the return value of the wait system call can be whatever the exit code was specified by the process which exited. Right? For example, if I said wait child by specifying its PID, so I said wait on child PID, and if the child had called exit with exit code 2, the return value of wait will be 2. If the child had exited with exit code 5, then the return value of wait would be 5. So let's look at this again. Let's say here's a parent. It spawns a child. Right? And now the parent makes a wait system call on the PID of the child. The semantics of the wait system call are that the parent will block, so it's not going to execute any other instruction till the child exits. Right? So till the child is running, the parent will keep blocked. As soon as the child exits, the parent will return from the wait system call. Right? So once again, wait is a system call, exit is a system call. The exit system call takes as argument an exit code. The wait system call returns as a return value the argument of the exit system call in the child process. Right? For example, if the child called exit 123, then when you return from wait, the return value will be 123. Okay. So once again, this is a method of inter-process communication. It is a limited form of inter-process communication. Only a child can communicate using wait exit to the parent, and only one number can be communicated in this way, right? So very small amount of data can be communicated from parent to the child, from the child to the parent. And the reason the UNIX system calls are designed in this way is to treat a process as some kind of a function call or procedure call which can have a return value. So for example, the exit code could indicate whether the program ran successfully or not, right? And the exit code is going to indicate whether the program ran successfully or not. So for example, on Linux, typically exit code of 0 implies success, right? And anything else indicates failure, right? Else failure. Plus the value of the exit code indicates what kind of failure it was, right? So for example, what a process can do is basically spawn a new process. So for example, if you say ls on the shell and ls failed for some reason, then ls can call exit and indicate the failure reason. So for example, you can say exit 10. The parent process, which is shell, can read the value return code from the wait system call, and it's going to say, oh, it's a non-zero value, it's 10, and so it can replace, it can print to the user, oh, ls failed with reason 10, whatever the 10 number means, right? If the exit code was non-zero. On the other hand, if the exit code was 0, then it can say ls succeeded, right? So that allows you to treat programs as procedure calls which have a return value. Okay, question is, how important or how significant is it that one process interacts with another process in the same system? We are going to see more examples of situations where two processes within the same system need to communicate with each other, right? It's very important actually. In fact, when you open your computer in a GUI mode, where you have a GUI, typically that's done using, the question is, how important is IPC or inter-process communication? Answer is very important, right? So I'm going to use the word IPC for inter-process communication, and let me give you some examples. All right, here are some examples. On Linux, for example, if you are, you're running Linux, then there's one process which is called the X window system. And now there are all the other processes, let's say browser, shell, and so on, which need to communicate with the X window system to display output on the screen in the GUI format, right? So X Windows is the GUI, is the program that implements the GUI on Linux, one of the programs that implements UI. And so here's one very important example of where one process needs to communicate to another process. So one process implements the display, other process implements the logic, and the process that implements the logic communicates to the process that implements the display to display things on the screen. And there are more examples that we're going to see in future. So it's very important. There's a question from OXCE. It says, how can process be changed with different modes? I don't understand this question. Maybe, okay, so we'll stop here and we'll open the floor for questions. Please let me know if you didn't understand or anything of that sort, or if you have any doubts. So we'll start with OXE, whose question I couldn't understand. Right, OXE, please ask your question. Okay, there's a question from BSARU.
Sir, good afternoon, sir.
Hello, good afternoon. Please ask your question.
Sir, if the output is redirected into a file and if the output is redirected to a file and the file already contains some data, what happened to that data?
Okay, good question. If the
And how do
output
I get
is
back that?
redirected to a file and the file already contains some data, then what happens to that data? It gets overwritten, right? So if you, for example, if you called open, then you initialized offset to 0, and so whatever you write to that file, it will get overwritten from there on. You can also open a file in append mode, in which case the offset will get initialized to whatever is the last value in the file, in which case it will just get appended.
Thank you, sir.
No more questions? Okay. Let me review what done today, just to make sure that we all understand. So we said, look, here is a process T. It can call fork to create another process called pchild, right? Pchild will have identical FD tables, identical FD table, right? Pchild can call exec, but if it wants to change its FD table, for example, to implement redirection, then it can say close and open and then exec, right? So this way it can manipulate its FD table before calling exec, before calling the new program, to change the environment of the new program. That's one thing we studied today, right? So these manipulate, change the FD table. So we saw how this can be used to implement output redirection and error redirection. Right? Example, ls greater than abc, or ls greater than out, or ls 2 greater than out. So if you have not followed this, I would highly recommend that you go to a Linux system and type these commands. Type ls greater than out and see what happens. Right? Then look at the contents of out. Then or type ls2 greater than out. Then look at the contents of out and reason for yourself why this is happening the way it is happening. Okay. We also saw that exit and wait can be used to do inter IPC, right? So exit code, we saw two more system calls exit and we saw a system call called wait. Process P1, so a child process, let's say P child, makes exit, so that will cause the program to exit, and a parent can call wait on that process, which means the parent will stop executing till the child exits, right? In which case, and if as soon as the child exits, the parent will return from the wait system call, and the return value of the wait system call will be the exit code as supplied by the child. Okay. Right. Okay, there's one question. PSGCT.
Hello, sir.
Hello.
My question is,
Please,
you spoke. My question is, you spoke system call. It replicates the resource for the child process, but how come the files are same?
could you repeat your question, please?
You spoke system call. It replicates the resources for the child process. So how come the files are
Okay, if I understand the question correctly, you're saying fork creates a new process. How come the files are same? Is that your question?
no, the resources are same. That is the files for which you create replicating.
Right. So let me repeat. So let's say this is parent. It calls fork, which creates a child, and I said that the file descriptor table gets copied, right? So whatever is the FD table here gets copied as it is to the child. That is the meaning of fork. That's the semantics of fork, right? So if FD table's entry is pointing to a file called out, then this FD table's entry is also pointing to the same file. Okay, the file doesn't get copied. It's only the pointers to the file that get copied, and so both of them will point to the same file. Does that answer your question? Does yeah. So would you say if that answers your question, or if you have a follow-up question?
Yes, sir. Is it for only for 0, 1, 2 entries or higher end?
No, it's true for anything. So even if this is 15, it still holds, right? The entire file descriptor gets copied.
Yes, sir.
Okay. How many thread and processes can be created by one application? So there is a limit that's so how many processes and threads can be created by one application? That's a question. There's a limit that's specified by the operating system, but for our purposes, we can say that infinite. But actually, there's a limit, and the limit depends on the amount of physical memory that you have. Right. So, for example, Linux will not allow you to one user to have more than 700 or 800 processes. Okay. All right. Let me give you a concrete example of how exit and wait are used. All right. So, for example, if I'm a shell, so let's say I'm writing the code for shell, right? What I'm going to do is I'm going to say while one, that's an infinite loop. I'm going to write to my standard output the string dollar and space of 2 characters, right? Then I'm going to read the command from standard input into some buff, let's say maximum of 100 bytes, right? And then I'm going to say PID is equal to fork, right? And I'm going to say if PID is equal to 0, which means I'm currently executing in child context. What am I going to do? I'm going to say exec whatever the command was, right? So let's say buff. Let's say the command was in buff. So I'm going to say exec buff. Actually, you're going to parse the buff to figure out what the command is and what the redirection is and other things, what are the arguments, etc. But let's just say exec buff. If you wanted to do any redirection, call close and open for redirection, right? As you saw. Else what it does is just called wait, right? And let's say it calls wait on PID. What am I doing here? The shell is saying wait for the child process to exit, right? So the shell just blocks, right? The shell doesn't show you the next prompt till the child process is exited, and that's what the wait system call does. It basically waits for the child process to exit before it goes back into the loop and prints the next $sign, right? So that's what wait is doing. Today I discussed that exit can return an exit code, and wait will get that exit code in its return value. And the shell may want to look at this exit code to do something. For example, it may say, oh, the process that I spawned failed or succeeded or failed for this reason, etc., etc. It may want to print a message to the user. Right? So in this code, we saw two things. One is that before I call exec, I can change the environment of the program by calling close and open to change the FD table. Also, I saw that wait can return a value, which is the exit code, which can indicate what happened to the child process, whether it failed or succeeded. There's a question from VPCOE.
Hello.
Yes, please ask a question.
Sir, how to redirect the output of a process to both the console and a file?
Okay, how to redirect the output of a process to both a console and to a file?
Yes.
Is that your question?
Yes, yes.
Okay. Well, interesting question. One way is that a process itself could say, I'm going to write to 2 file descriptors, right? So whatever it writes, it's going to write to 2 file descriptors. Let's say it always writes to file descriptor number 1 and file descriptor number 5. So you can redirect 1 to console and 5 to file, and so whatever is getting written will be written to both sides, the console and the file, right? But the process needs to be written to make 2 system calls now, 2 writes. One to file descriptor number 1 and second to file descriptor number 5. And if the environment is set up such that 1 points to console and 5 points to a file, then you get what you wanted. Does that answer your question?
Hello.
Yes.
Sir, if a particular say for a command is giving some output, then how to redirect that output to console and a file both? I cannot make the change.
Okay, so the question is, if one program is just giving one output, I want to redirect the output to both a file and a console. How do you do it? Well, there is so I'm going to show you some more examples of how redirection works, at which point it's going to become clear. But the short answer to your question is there's another program that can do it. All right. So the way you do it is, let's say this is your program ABC, and it is directing on a standard output. There is some fields that are coming, right? So what you can do is you can feed this stream to another program called let's say DEF, And this program is going to have two streams coming out, one on file descriptor 1 and another on file descriptor number 5. And both of them are just going to copy these streams, and one of them could be going to a file and another going to a monitor, right? So actually on Unix there is a utility called T, which allows you to do this, right? But we can discuss this as we talk more about pipes and all that later, right? So right now we are not, I don't have a, based on what we have discussed so far, it's not possible. But if based on what we're going to discuss in future, I'm going to show you how this can be done. Okay, if there are no questions, it's time. I would basically say that all the lecture material is available on the course web page, and I have a sense that maybe people are not following the lectures completely. So I'll highly recommend that you do some exercises that are given on the course web page. All right, so that you are able to follow these lectures better. Also, what I will do is I'll post some videos of my lectures online. Also notice that all the lectures that we are doing on this AView software are also available as in recorded form inside the AView software on your local sites, right? So please feel free to go to your local AView person and ask him to give you the video of the lectures that we have been doing over the internet. Okay, thank you.